And today, I would like to talk about the machine learning and lattice QCD based on the, what I have been done in recent years. And I will talk about the neural network part and neural network as a first part. And I will tell you the our Julia code for lattice QCD that's intended to use the machine learning and lattice QCD. Oops. And okay, this is just a start. And as you already know that neural network and with expert knowledge beat some traditional method in natural science. The panel on the top is the score of the quality of the protein folding problem. And the neural network method achieved the best score in 2020. And this is based on the language processing model, but it's beat the traditional method. And the panel on the bottom is the quality of the wave function for many body system. And EPS and the PEPS is the network, method based on the tensor network. And that solid line indicates that the quality of the, actually variational energy of the neural network wave function. And it achieved the highest score. So that means that we should use that neural network and combining with the expert knowledge, and then we can go next stage. And neural network itself is very easy to understand because that's just a combination of the linear transformation and the nonlinear transformation. We know that works, right? And the first equation, z equal w blah, 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 is called affine transformation. This is an extension of the linear transformation. And the difference is that we have vector b in the equation. And the other part of the neural network is that the nonlinear transformation that is indicated by sigma. That is nonlinear function like the hyperbolic tangent. Then we can combine them again and again. Then we can get that fully connected neural network. So the input is a vector x and multiply with the weight matrix w and proceed that procedure again and again, and you will get another vector. That is the output. And neural network makes that map between the two vectors. And in the physicist terminology, this is just a variational transformation. Transformation parameterize the several bunch of parameters. And I have an example of that. So that's the image recognition problem. So first, we input an image that is converted into a vector. That can be done because that image is just the array of the pixel values, and then we can make a vector from that, and then we can input that vector to a neural network, and the output is that in this case that is a 10-dimensional vector that indicates a percentage of the what is the input. In this case, that output should be a vector for 2. And we have a fact that a neural network can mimic any function in any precision. This is so-called the universal approximation theorem. And so this is a very powerful way to parameterize a function. So in this, for example, neural network mimics the map between this image space to a label space. This is 10-dimensional vector space. And neural network helps that data processing. And in this case, that this is a face recognition. And if we combine that the neural network to the expert knowledge, and we use that, you can use the neural network in this natural science. And a neural network helps the data processing, like the AlphaFold 2 or neural network wave function. However, the Lattice QCD, it has more complicated data structure because that it is the four-dimensional field theory and the non-abelian gauge degrees of freedom and non-abelian gauge symmetry, and also we have fermions, and we want to have a exact algorithm. So while neural network is just approximation, so how can we deal with the neural network? And so we know that the gauge covariant way of the data transformation of the gauge configuration, so-called smearing. So we input a bearing or a thin link, and we can construct fat link through a summation of the thin link plus a staple. And with this projection, we get a smeared link. And we found that actually we can tune this parameter by backpropagation, which is used in the neural network training. And actually, they have, neural network and also smearing has a similar structure. First, we summing up the input data and transform non-linearly pointwise, and then we get the output. So we can use that same idea for this new types of the neural network. So we call this one as a gauge covariant neural network, which parameterize that map between the gauge configuration to gauge configuration. And of course, we can stack this structure as a, usual smearing. And yes, and we have an alternative realization of the gauge symmetric neural network that is so-called gauge equivariant neural network. That should appear in the next talk, I think. And this is a comparison between the conventional neural network to the gauge covariant neural network. The input is an image that processed through a convolutional layer, and we have distorted image or extracted image, and that fed in the dense neural network. Then output is some kind of label and compare to the answer, and that should just should feed back the difference of them, and we can update these parameters. And our network has a similar structure. First, the input is a gauge configuration, and that fed in the covariant neural network. And the output is a distorted gauge configuration. And we can construct a Wilson loop or fermionic action using this distorted one. And we have the parameterized action. And we can compare them, and we can train the parameter in this network. And this is a comparison or a dictionary to our neural network to the conventional neural network. And the input is an image, and in our case, it's a gauge configuration. The output is again image or some vector, and in our case, this is the gauge configuration again. And the convolutional neural network keep the translational symmetry, and our network keeps that translational symmetry and the rotational symmetry on the lattice, and also gauge symmetry. And if you use the neural network with fixed parameter, it acts as the image filtering. And in our case, that works as a stout or up smearing. And most important point is that we can do a training. So in conventional case, that is done by a backpropagation and the data rule. This is basically the chain rule of the in the calculus. In our case, we can in our case we extend this kind of rule for the gauge symmetric data, namely gauge configuration. And we want to examine our idea, it works or not. So we invent a new algorithm for that, and actually for lattice gauge theory. So gauge covariant neural network can mimic the gauge invariant function, and it can be used in the simulation actually. And we use that self-learning hybrid Monte Carlo. The panel on the top is the schematic picture of the HMC, and HMC gives that a bunch of sequence of gauge configurations through molecular dynamics. That is, they are fictitious dynamics using that QCD action. And in our case, we use that similar, update algorithm with the, approximated action. And this approximated action is parameterized with the that gauge covariant neural network. This, you can understand this as the adapting relating method. And we try to produce a gauge configuration using this algorithm. So final target of our algorithm is that generating overlap configuration using domain wall action with this kind of parameterization. But in this case, we try to generate configuration using the staggered fermion versus staggered fermion, but their mass are different. And this is the final slide of my first part. And this is a bracket and a Polyakov loop and a chiral condensate. And different color indicates that a different algorithm, but they are mostly overlapped. And of course, this self-learning hybrid Monte Carlo is an exact algorithm, so this is expected, but we got consistent result with the HMC. And these results are obtained by our code, Lattice QCD.jl, and I will explain later. Self-learning. Because that, okay, good question. So let me see. So self-learning hybrid Monte Carlo itself is an exact algorithm. And this can generate training data. So this algorithm can generate own training data. So in this sense, this is a self-learning hybrid Monte Carlo.
Because mental coding
yes.
itself is like and so that's what you call the lab.
I'm sorry, could you say it again?
I don't know.
Yep.
Self-learning.
Yes.
So you use the data generated by yourself and to adjust your parameters.
Yeah. Something like that. Because that generated data distributed as a QCD probability distribution, and this algorithm can use that generated data by own. This is kind of self-training, right? Okay. Okay, now I will explain that our code. And so I will explain that Lattice QCD.jl and Gomarizing flow.jl. And first, I want to explain that what is Julia. Julia is a new types of the open source scientific language, and this uses that just-in-time compiler with LLVM backend. And the important part is that this is fast as C, and also the practical as Python. And also, this is a machine learning friendly. This table is at comparison of these languages. So the top one is Julia and the C language, and Python plus number. This is the how to say accelerator using the JIT compiler, and the compiler uses the how to say this is just-in-time compiler with LLVM technology, and the C has a compiler called Clang. This is also based on this LLVM, and I will show the code later, but I compare that numerical performance of these languages, and Julia has a similar speed to the C language. And this, how to say, the variable are dynamically or statically typed, and also this support the parallelism and GPU. And this is a code. This is a code of C and Julia, and I omit several unimportant parts. And these are just a vector, matrix vector multiplication. And I implemented the complex 12 times 12 times complex vector, 12-dimensional complex vector, and I repeat it many times and take average. And as you can see, that the code of Julia looks like Python, short and also simple, but fast as C. So the time is at 0.0014, and C in the case of C that 0.033. So single core performance is similar. And why I choose Julia? So this is my personal opinion. So at least that this is a modern scientific programming language, and easy to make a code, and fast as C or C++. And Julia and C both use the LLVM backend. And fewer compiling or dependency issues. You can see, so I always experience that, how to say, if I download a open source C code, I cannot compile. But in case of Julia, I just execute it. No explicit compile is needed. That is important, I think. And the third part is many people are potentially interested in that. So more than 400 people are registered into Julia in Physics 2022 online workshop. And also I find that more than 5,000 public repository in the GitHub. And no two-language problem. So we usually encounter two language problem, right? So that is the fact that while the users are programming in high-level programming language, such as R or Python, and the performance critical part has to be written in C or C++ for performance. So we have to rewrite our code into C++ because we need speed. But that is a problem because we always make a problem that could occur the bug. So we should avoid this situation. And Julia supports the neural network and also tensor network as well. And this works on the Xeon, Radeon, and Apple Silicon, and the A64FX as well. And they support MPI and GPU. And this is a schematic picture of what is done in during the compile time. So Julia has our own compiler system that generates some, how can I say that, intermediate representation of the code, and that fed into the LLVM backend, and that generates a binary. And that binary works on each, how to say, architectures. And the C, actually, this is almost the same as C, because the C also has a Clang compiler that generates LLVM IR, and that's converted into binary and work on these architectures. And somebody already tested on the MPI performance on Fugaku, And this is the send-receive performance, and different colors indicate a different language, Julia and C. And they follow the same curve. And this is the all reduced performance, and this also, follow the same curve. So that means that Julia has a similar scaling of MPI with C language. So I mean that no obvious overhead there. So we made a code on Julia. So this works on laptop, desktop, Jupyter Notebook, and supercomputers. This supports a lot of algorithms, and especially we implemented self-learning HMC. And you can start this code in 5 minutes. This is very easy. And this is an overview of our code. So Lattice QCD.jl is actually a wrapper of these lower level codes, QCD measurement and lattice Dirac operators, and gauge field.jl. This supports that infrastructure of the Lattice QCD. And I think I want to emphasize this one. So this supports that the symbolic operation of the Wilson loop and the Polyakov loops. And we implemented the semi-automatic differentiation of the gauge link using this Wilson loop.jl. So some of them are used the automatic differentiation of the gauge link. So we usually have a problem to derive the equation for force equation for the HMC, but sometimes we can skip that once. Okay. And this is a comparison. This is a performance of our code on MPI with MPI. The horizontal axis corresponds to the number of processors, and the vertical axis is the speed. And the left panel for the absolute execution time, and the right panel is a relative speed up. And as you can see, that the scaling looks well. But this is not enough for bigger machine and a bigger system, and we need. So actually, we just make this code by 2 people, so we need more contributors. Please help us. And this is the last part of my talk, and I almost skipped this part actually, because I believe that Nobuyuki Matsumoto will tell us the detailed things of this kind of thing in February 16. So I want to explain that about the normalizing flow. So normalizing flow is that in physicist terminology, this is a trivializing map with machine learning. And we have trivial probability distribution, and we have probability distribution for quantum field theory. And if we find a map between them, one-to-one map between them, we can go and back, right? And we can generate configuration using the trivialized configuration, and we can get the non-trivial configuration through this kind of map. And some people in MIT and Google DeepMind realized this kind of map, so-called using normalizing flow. And they call that is a flow-based sampling algorithm. And the idea is very good, and that we need to test, right? And to do that, we made a public code of that. We named that normalizing flow. This is a public Julia code for flow-based sampling algorithm for scalar field. This only supports the scalar field for now. And this supports not only 2D, but we support also 3D. And this works on CPU and GPU with Docker. And we did some research using this package, and we invent new types of the convolutional operations, which improves the acceptance rate of this kind of algorithm. That's actually, in this case, that means that we can make that autocorrelation shorter. That is presented in the New Lips 2022 workshop. New Lips is the biggest workshop in the machine learning or deep learning research area. Okay, so this is my final slide. So I gave talked this kind of ideas. And first part is a machine learning for Lattice QCD. So neural network plus expert knowledge gives the best performance. And neural network can deal with 4-dimensional non-aggregate symmetry. And the self-learning hybrid Monte Carlo with HMC works for dynamical fermions. And the second part, I gave a talk on the Lattice QCD plus machine learning plus HPC with Julia language. And Julia has a similar speed with C, with or without MPI. And this is machine learning friendly. And I made 2 calls for lattice field theory. One is for Lattice QCD, and one is for 2-dimensional scalar field theory, or 3-dimensional field theory with trivializing map. Okay, that's all. Thank you.
Thank you very much.